You guys may not know what an actuary is. This is the Actuaries Institute you're in, and it's a professional body that supports the profession of actuaries. Us as actuaries, we measure uncertain things, we set assumptions, we do a lot of investigations, and that's kind of where our line of work crosses over a bit with data science. So that's why we've hosted this event here, so we can learn a bit more from what you guys do. And if you guys want to ask what we do, we can tell you that too. And I'd like to introduce first Eugene, the founder of Data Science Sydney, and he'll introduce the speakers for today.
Thank you very much, Aidan. And welcome to one and all, yet again, to Data Science Sydney, now running in its 10th year, 11th year maybe, and over a year in this wonderful venue here in the Institute of Actuaries. So big thanks to the Institute for being such wonderful hosts and for supporting us for a year now, and bringing us back from obscurity in the 3 years in the COVID period when Data Science Sydney didn't do much. And quite a few things happened in that period of change, that COVID period, one of which was the advent of generative AI, which for many of us has been, well, certainly life-changing in a career sense, in a view of the world sense. Yeah, for many of us, I think it's been literally life-changing. And as you've seen, for those of you who've been coming regularly over the last year, this topic of AI, generative AI, has been a very important part of what we've been doing here at Data Science Sydney. So it is for this reason that I want to let you be the first to know that we'll be doing a little bit more of a rebranding to better reflect what this meetup is about. So henceforth, we're going to be AI and Data Science Sydney. Anybody wants to discuss this or has a view on this, get in touch. Come talk to me during the break. We can talk, but that's what's going to happen. A few other things. One is that, just a reminder, we do announcements at the end. So I want to say that now because usually as soon as the second speaker finishes, everyone is racing off to go home or grab the remaining pizzas. I don't blame you on either, but please hang around after the second speaker in case there are any folks with announcements. Now, this brings me to the first speaker, Jack. And I have never met Jack before. And as you know, usually when I know the speaker, I will say something about them a little more than what we have in the bio. You know, the bio is pretty plain and serious, and I'd like to say something personal. The one personal thing I'll say about Jack is I was really impressed with with his initiative, because what he did was he just contacted me on, I think it was on the Meetup Messenger, first of all, and said, hey, I've got this presentation. Do you think it's interesting? And I think that's great. And I bring that up, A, because I wanted to say something about Jack more than just what I have in his brief bio, having not met him, but B, to let you all know that that is a good thing to do for you and for Data Science Sydney. So if you have something to present, don't be shy, get in touch, and you'll probably get a chance to get up here and present it to the group. So without further ado, let me tell you about Jack. So Jack Simpson is a director of Endgame Economics, a firm that specializes in providing quantitative advice in the energy sector. Jack has over 10 years experience working as a consultant, data scientist, and an academic researcher. He holds a PhD in computational biology from the ANU. Jack's talk, as I'm sure you know, will be on optimization, specifically linear and possibly mixed integer optimization, and applied but not limited to the energy sector. Over to you, Jack.
Thank you. Yep, come here. Hey everyone, thanks so much, Eugene. Is that a bit better? Yeah, so let's see if this clickers. There we go. Cool. All right. So yeah, I guess following on a little bit from Eugene's intro, I work at Endgame Economics. We're a firm that focuses on all things energy, going from how much coal power stations are paying for their coal, all the way through to what happens when you plug your light in at the outlet. And yeah, I've had a bit of a funny career route. I started off in computational biology, working on honeybee behavior, went into generalist data science consulting, and got kind of used to just jumping around between projects and industries where the problem was, how do I find the data? How do I fix the data? And when I bumped into energy, I suddenly found I had more well-structured data than I could ever dream of. And I've just been, I think for the last 6 or 7 years, I've been absolutely fascinated by the energy sector. And also the fact that these data sets are pretty much all publicly available. Like the data set I mentioned there with billions, hundreds of billions of rows, that's everything that happens in the energy sector for every power station on a 4-second basis going back decades. The other thing I think that has also inspired me about energy is I bumped into this new technique. I'd been used to using machine learning in my line of work, but suddenly when I came into energy and I really wanted to understand how are power stations dispatched, how does the sector work? And suddenly I started getting told of this concept of mathematical optimization, linear programming, mixed integer programming. And I'd never seen it before. I spent a bunch of time trying to understand it, and now I use it every day. And I thought that since I'd never seen it before, and I've met other data scientists who had never seen it before, it's actually quite a useful problem-solving approach that often we use ML to solve, and sometimes ML is, for a lot of problems, is the ideal one, but linear programming is actually a really powerful approach that most people haven't heard of that I'm keen to talk about. So yeah, that was really the idea, give you a bit of an idea about the energy sector and hopefully give you an understanding about the types of problems linear programming can work well with. So I guess for a little bit of context, you guys are probably seeing energy in the news, and that usually means there's problems or challenges in it because otherwise it's quite boring to most people. And so what we're at the moment is really the start of this energy 20-year transition of the sector, where their aim is to retire all this coal and gas and bring in renewables and storage and build out a whole bunch of transmission. And we use linear programming to figure out how we optimize that mix of build and plan out the roadmap for that transition. That this figure over here, this is a graphic that the Australian Energy Market Operator puts out, looking at saying this is what we think the power station mix will look like going out to 2050. So I guess to jump a little bit more into that, you're probably wondering, what is the NEM? What is an energy market? Well, basically, every power station from North Queensland all the way through to Tasmania and South Australia is all connected into one big interconnected system we call the national electricity market. And you can actually think of it as both like the physical system, like the electrical engineering and the poles and the wires, but it's also a market. And really, the kind of mathematical mechanism that connects the two is a linear program where prices are set based on the bids that generators submit on a 5-minute basis. In fact, like these very lights, there is a price for this current 5-minute period we're in right now. There was a price that was set by a linear program, and at the end of this interval, there'll be another optimization that will be run that will factor in the real-time bids of power stations, and that will set the price for the next 5 minutes.
Jack, for the record, it was $58.02.
I won't go too much into this, but this is what some of the bidding data can look like from a power station, where you effectively have the price bands that they submit, and you will then have the availabilities of power that they are willing to sell in those bands. One of the fun things about the market is because it's so open, of course, in real time, they won't, you don't find out in real time what the prices are so that the generators have to operate independently. But you can, at the end of the trading day, you can basically go in and look at what every single power station bid, rebid. You can see almost everything. So I guess this gets me into this area of mathematical optimization. Like, what is this linear program that I've been talking about? So really, it's a way to mathematically craft the rules for the system. So instead of with machine learning, where you're providing historic training data and your program is really learning the rules from the system, you're basically defining the constraints and the variables that will describe the system and interact to lead to an outcome. The thing we've also noticed about this is that in the way that machine learning is incredibly powerful at making forecasts about the future, linear programming is really useful once you have that data at determining, okay, what should I actually do with my asset mix? For instance, the very thing that I just described about prices being set in the energy sector, there is a neural network that gets run every 5 minutes that forecasts what demand will shift to at the end of the next 5-minute interval. And that data gets plugged in along with the bids into a linear programming describing the actual grid system. And then from that, it will then produce the pricing output, but then also what every single power station should be doing for the next 5 minutes. And this linear program, oh, yes?
Question while you're going. How accurate is that 5 minutes? I'm assuming it's very accurate, seeing you're only 5 minutes out.
Yes, it's not hugely inaccurate. It was a neural network that was built in the 90s, so there's probably some new things that could be done with it.
So is it 99.9% or sort of 95s?
I'm not sure what the accuracy, especially because there's other mechanisms that will correct for it as well. But we definitely, we've seen people propose methods that are more accurate than it, because really the neural network, its inputs that it takes are, it effectively looks at what the change in demand has been for the 5 dispatch intervals leading up to that one, and then it looks at the same time from a week ago, and then it predicts the change. So there's potentially room there to factor in things like, the weather and solar and things like that as well. And yeah, so I guess there's really 3 core components of a linear program that you'll be kind of thinking about when you're structuring these optimizations. So the first thing is you'll have an objective function. Fundamentally, if you think you've got a program that could be solved with a problem that could be solved with this approach, you're really thinking about, is there something I'm trying to minimize, and is this or maximize at the end of the day? So in energy, a lot of the time, you're trying to minimize costs or maximize profits. You have variables that will be things like what you're trying to dispatch a power station for. These are really, you're trying to ask the program, tell me what the optimal value for this variable should be. And then, of course, you actually have the constraints for the system. Things like what the upper limits of generation of a power station. Oops. So I think I just described most of those things, so I'll just jump to the next one. So I thought the way I usually find things that are a bit more tangible is I usually build simple examples of things to make it a bit more understandable. So what I thought I'd just take you through is a very simple linear program. We're going to take 2 power stations, and we're going to dispatch them so that supply and demand match each other exactly. That's a core constraint of the system. You don't want to generate too much, because that creates problems. You don't want to generate too little, because then, of course, you get blackouts. You have, of course, we've got constraints in terms of the limits. We call them ratings of the power stations that they cannot exceed. And, of course, different power stations will have different fuel costs. Some power stations, like wind, don't have a fuel cost. Others, like coal and gas, have different fuel costs. So in this case, very simply, you imagine we have to dispatch for the next interval. Demand is at 1,000 megawatts. You can kind of just ignore the units, just think of them as the numbers. That's what we have to dispatch a coal power station and a gas power station to meet. And really, there's 3 attributes that are material to these power stations in this optimization. we need to figure out how much we're going to dispatch them for, which we don't know yet. There's a rating, an upper limit for the power station that is actually set, that it can't go above. And then there's the actual cost to actually run the power station. So per unit of generation, how much is our fuel cost to build? And we're just assuming that the power station is bidding in at its fuel cost. So the first part of this is, if you recall, there were three parts: the objective function, the variables, and constraints. So we have the variables. Those are, of course, the optimization is going to figure out how much we should actually dispatch both of these power stations for. In our case, we've just defined these as being continuous variables. You can actually, there's flavors of, if you go into mixed integer programming, then you can have integers for binary or integer variables, which are very useful if you want to make, have conditionals or have decisions about things. So for instance, you can have variables that tell you whether you want to turn off a power station. In this case, we've just got continuous variables, and I've set them to a lower bound of 0. In fact, I think because we don't want to have the power stations generating negative. I once pulled this optimization together and forgot that last part, and the power station and the optimization just dispatched everything at a negative value to really max, because that made the system actually cheaper in it. So sometimes you get funny outcomes unless you're across all the constraints. So that's the variables for this optimization. Now, the objective function is we're trying to minimize the cost of dispatch, which comes down to the fuel cost. And I've got to point at this thing. And so in this case, we've got in the earlier slides, I created my coal generation variables that are the optimization variables, and I just multiply each one of them by their cost. So effectively saying, for every unit that this coal unit generates, it's costing you this amount of money. And I'm telling the optimization to minimize the total of this objective function. These objective functions can get enormous, and they can incorporate things like fixed costs, build costs as well, but yep, we're just sticking to this for now. Finally, we have constraints. And we've got our demand constraints and, of course, our upper limit generation constraints of the power station. And they just look like equality or inequality equations. So you can see over here, we've just said the sum of the coal and gas generation has to be equal to demand. And then we've got constraints that are saying you have to be less than your maximum rated capacity. This is one of the things I really do quite like about linear programming, is you have quite fine-grained control over the nuts and bolts of the system of your optimization. So when we run optimization, when we run the optimization, of course, this is quite a trivial thing. It'll basically say the variable for our coal was dispatched for 800, gas was 200. We have, and of course, we've now satisfied that demand constraint. And in this case, this is trivial. You could have just, calculated this by aligning them based on cost anyway. But you can imagine that once you have hundreds of power stations and tens of thousands of constraints reflecting transmission, suddenly it becomes a bit, not to mention the effect of batteries and pumped hydro. It can be quite complex extracting what you should actually do with the system. The other thing I really wanted to point out about this example is the linear programs give you the ability to interrogate the constraints in your model. And sometimes we see people who don't necessarily need the model because they want to get this optimal outcome to decide what to do, but they'll build it just to understand what constraints are in their system. So they'll build an optimization to represent their factory, but they're using it to understand the effect of different bottlenecks on it and what they should actually focus their effort on. So in this case, I can look at the constraints. I can ask the constraints to tell me things like the value of the demand constraint, which is, of course, $500. And you can think of the value of the constraint as what it means if you were to add one additional unit to the right-hand side of that constraint. So in that case, if demand was 1001 instead of 1000, what would it cost to satisfy that additional unit of demand. And in fact, that is genuinely the way that the electricity price is set in the sector, that by looking at the demand constraint. The other thing you can also do is looking at some of the other constraints is I could look at the value of that coal rating constraint, which is negative $400. And so in that case, by adding 1 unit to that constraint, it makes the system cheaper. If you had more coal, you don't have to dispatch gas as much. So that's actually telling you that there's certain constraints sometimes where if you can do things to that, it might actually be beneficial for the system in a different way than just relieving it. And you can also look at how much slack there is in constraints. So you can see if a constraint may not be binding, but then you might be interested in this case, it tells you that you had 300 more megawatts of rated capacity in your gas unit to dispatch if you had needed it, if demand had been higher. And we will often spend a lot of time digging into the constraints that come out of the 5-minute dispatch optimization, because it'll tell you a lot of things. And some power stations will even be clever enough to know that certain constraints binding will affect the price or will affect other generators in certain ways and will shape their bids based on their understanding of how these linear programs work. That was just a little example. So the bigger, like the complete NEM model has hundreds of power stations. We'll run it out for 20 years. And a lot of the time we'll also use it to make build and retirement decisions, because in the same way that I think I showed you, you can have these rating constraints, you can even have variables sitting on the other side. So it's actually not just limiting the generation, but it's deciding how much should I actually build of this power station as an upper limit. It's co-optimizing that as well as dispatching the power system. And there's, depending on the granularity that you want to go to, as well as representing the system, you can factor in a whole variety of additional constraints to represent just the different features of the different power station types. So, you know, of course, you've got wind and large-scale solar, which will have changing rating limits. And you'll also have batteries and gas and other new technologies coming in. And so we'll often have to represent things like you'll have a constraint that might say, well, this coal power station is either turned off or it's generating this amount of power. You can't go in between that. And also you can have, of course, constraints. You might say, the optimization might tell you, you should build this amount of wind over the next year. But you might actually know, realistically, it is impossible to build that amount of wind in 1 year in this country. So you might actually say, well, there's a hard constraint on how much you're allowed to build every year that passes. Just one of the things I did notice is there's a few industries where linear program is used a lot, but because it's been around, like a lot of this stuff came out of the 40s and the 50s, and it's been getting good every single year. So it's part of the furniture in a few industries, like most airlines. That's how they're optimizing how they dispatch. They schedule their flights, and also staff, mining, transport, pretty much supply chain. In fact, one of the things I like to say is that the reason electricity is so interesting is that it is a instantaneous supply chain. Supply and demand have to be constantly met in real time. Even water uses is actually quite similar to electricity market optimization in a lot of ways. So there's a lot of sectors where a lot of people, it's used extensively, but most people just don't bump into it. And occasionally we'll see people building recommendation engines to make decisions where you'll suggest, you know, you could do this really simply if you turn this into a linear program. I thought I'd just summarize a few broad topics that, in case anyone in the audience is thinking of any problems at the moment, and this may suggest that if it meets some of these criteria, potentially you might be worth looking into LP. So fundamentally, we're maximizing or minimizing. I guess a lot of optimization is that too. One of the benefits of linear programming as well is you don't actually have to have historic training data to run the model. In fact, I've got a couple of models doing short-term price forecasting that are machine learning models. And because the sector's changing so much, coal is getting retired, new renewables are coming online, you have to be really careful with how generalizing from the historic data into the future. For example, I remembered when they retired a big coal power station, coal normally bids in quite cheaply compared to gas. And one of the features in the model was the availability of scheduled generators like coal and gas. And in response to this coal unit shutting down, a whole bunch of gas power stations declared that they were available. So my model was like, oh, there's heaps of scheduled generation. The price shouldn't be that high. But because it was composed more strongly of gas units bidding higher, you got like this different outcome based that the historic data would suggest. The other big thing too is, do you have a lot of complex decisions you have to make about things? So a lot of variables or constraints. A big one too is if you want to have that fine-grained control of constraints where the model cannot violate something, and the model would rather say that a problem is infeasible and impossible rather than violate hard constraints that you set in it. Finally, and I think this is also a thing we use the models for a lot, is sometimes we use them just to understand the system better. So we build these large market models, but all the uncertainty is in the inputs of them. We don't know for sure what a gas power station is going to bid into the market in 2050. We don't know for sure how much a wind farm is going to cost, and we don't know whether a whole bunch of government schemes, what's going to happen with them. But what you can do is you can use these models to really look at the 10 different worlds that materialize and go, if these things happen, then this is the likely interaction of all these variables. And because everyone's making announcements and things are happening all the time, the future out to 2050 is just constantly shifting, which is why it's quite fascinating too. So yeah, I guess I'll stop now, but really, yeah, come have a chat with me if you've got an optimization. If you think you might have an optimization problem, I'd love to like chat with you about that. We're running a little optimization meetup that we meet every couple of months, just focused more on linear programming and mixed integer programming. So if you've got a problem you think might be interesting in that space, or you want to give a talk and you've done this type of thing before, we'd love to hear from you. Thank you.
Any questions?
I'll ask one. It might be a bit of a curly question. This is about a market and optimizing in the market, but there's other players in the market who are the generators. And as I understand it, I think this is going to work. As I understand it, the prices or the costs that the generators set are up to them.
Yeah.
They're in the game to make as much money as they can, and the national energy market is the opposite of that, to provide an optimal supply at the best cost. Do you have any access or any prediction capability of what the participants are doing, meaning the generators are doing, around pricing and cost?
As in at the moment, or into?
Or ever.
I mean, we definitely know how they're using their portfolio and bidding in, and you sometimes can see people wielding market power in certain ways to drive certain outcomes. I think I used to blog a bunch about this, and I once saw an interesting thing happen with the pricing, and I was going to write a blog post on it, and Oliver called me and said, don't write this unless you want to get sued. So there's definitely that, and there's an interesting dynamic where you're right, with a lot of the long-term modeling, we're trying to minimize costs of the system, but whereas if you're an actual player, you're flipping this optimization and you're like, I'm trying to maximize my profits in this case. There's usually with these things, we will incorporate, we'll look at run models where we just have the bids coming in as short run marginal cost, or we'll incorporate some bidding information that's kind of static, just to make it easier to interpret. But a lot of this stuff, of course, like is unknowable, like what demand will be at this point in time. But I think it's really so that you can really test what the impact of different projects will have in the longer term. That's the reason. Because fundamentally, you'll have people will dream up ideas, and of course, you can put any number you want into these, but you have to stand by your assumptions for them. So, and sometimes people will say, what if we put, we give out this amount of money so every household can put a battery of this size in their house. What does that mean for the system? And then we can run it through this and go, well, it would probably cost this amount of money and have this benefit to the system, but this is a lot of money. There may be cheaper ways. We can test whether there's cheaper ways to achieve things. But there's a whole area of kind of the Nash-Corno equilibrium, like economic, like you can factor in certain opportunistic bidding into the models, but then it's also a trade-off in terms of how realistic is that, and makes the models much harder to interpret as well. Sorry?
Can you hear me?
Yeah.
Yeah, you mentioned that one of the things that makes energy markets so interesting is that supply and demand have to be matched all the time, and that's one of the reasons why we have such big price spikes when there's a very large demand and it takes a while for generators to come online. So my question is, now, since Tesla has come around and improved battery storage technology, that's becoming less of a constraint. So do you see improved battery storage as a significant driver in changing the market dynamics? And this accurate demand generation potentially is less important because we can do better battery storage?
So batteries are really interesting. I think the primary challenge with batteries is really the long duration of the system. So when we look at some of the historic wind and weather patterns, the challenge comes down to how do you get enough storage in the system to get you through a week or 2 weeks of low wind and solar activity. That's still, in a lot of ways, that there's a huge amount of storage we have to put in the system. The Tesla batteries and these other ones, they have actually played in this area of the market we call ancillary services, which is all around grid stabilization, but not long-term kind of duration of the system. So they've been phenomenal at doing that. But what we think is going to happen is a lot more storage is going to have to be built in the system to shore it up, especially that deeper storage. That's partly what, despite a lot of the delays, Snowy 2.0 has been about. And I've got a friend who actually works for a battery company, and they think that in the future, there'll be increased volatility and opportunities for batteries to take advantage of that. So storage, if we continue to move to a renewable system, the deeper storage is going to become incredibly important. We need to build a lot of it. That's right.
Thanks for the presentation. I was just wondering, is there a variant of mixed integer or linear programming that takes the relationship between different entities or nodes or providers into account? Like, can we think about these power stations and a network that the edges have meanings and have weights, and this relationships mean something? And then is there specialized models that solve that?
So we often call them nodal models in the energy market, and you're right, like where we'll actually have, in this case, a lot of the time we think about demand at the state level, but usually you have nodes of demand and nodes of generation, and you'll have constraints that can represent the limitations of transmission in the network. So we don't have nodal, there's been a fight to bring in nodal pricing in Australia and have the model accommodate that for a good few years. Places like Texas and pretty much New Zealand have that. Like here, we pretty much have one price for each state in Australia. New Zealand's got something like 256 prices where they've done that more kind of nodal representation of the system. So you can represent it in that way with a mixed integer program. Yeah. I'd be happy to chat more about that to understand that. I think there's people that do that type of thing, and a lot of times you use the constraints to carve out that relationship.
Thanks for your presentation. My question here would be, how do you do your evaluation to optimize the results, and how do you define what is the true value?
Oh, how does it actually do it?
Yes, like how do you define the true value, and how do you evaluate your optimized results?
So the way that the system works is you'll turn it into this mathematical equation, right? And then you pass it to a program that's called it's called a solver. And effectively, trying to think of a good way to describe it, but it turns it into like a giant, how would you describe, what's a better mathematical description of what it does?
I'd say what you're doing is defining the problem and then you're finding the mathematically best answer of the objective function. So it is, in the terms that you define it, it's the lowest possible cost. So the question becomes how well you define the problem to represent the system.
Because the solver problems effectively, it uses the upper bounds of those constraints to then search out, like, it almost turns into a giant polyhedron, and then it looks for the upper bound of the constraints. And once it hits a certain point where it can't get a better answer, it actually finds the globally optimal solution.
Yeah, I know that. Thanks. But my question here would be focusing on, for example, when you build a model, you have lots of assumptions, and when
you mean about the energy market models, like?
For example, you have the optimized results. For example, you maximize certain parameters. You believe that this is the maximum based on equation and the assumption you have.
Yes.
But how do you compare this one with actually the true value that may or may not even exist? For example, when you're saying that you need to use X amount of product to making this kind of code, and this amount of code is the maximum energy you can generate. However, how do you know that what's actually the maximum energy you can generate?
Oh, the limit of the power station?
Yeah.
I got the answer for you. You don't know.
You don't know.
Yeah.
You don't know. We don't know what that true number is.
I mean, if it's an existing power station, you know the rated capacity, but if it's a future one, you don't.
But we don't know what the right answer is. What we do know is that if we define these things and we choose a random solution, we can show that if we were doing this thing with someone just sitting there with a pen and paper, that we might get a 20% improvement versus that over time. So all of these problems are about working out, you define a problem in a set of terms, and then you work out how much better that solution is than the one that you might have come up with otherwise. Yeah. Which is really what the whole of optimization is about. But as to the question of what the true best solution is, well, we're always in search of truth.
Yeah. When I came at this from the data science angle, Oliver's actual mathematician, so he understands. The maths of the solver programs is just mind blowing. The people working on that, yeah.
You have this problem of well, the data reflects one situation. Once you get into what if territory, and when you're trying to find the best what if, and you're optimizing. So yeah, machine learning is whether your base model is built for machine learning or it's linear equation, is linear optimization. Yeah, you don't know. There is no spoon.
Just a question about frequency control and ancillary services and game economics. Do you do any work on trying to work out optimization for frequency control?
As in playing with the causa pays data set side of things?
Yeah.
And
if so, like, can you share some findings, because that's a really volatile element of the electricity market.
In terms of prices in those markets, or?
Yeah, price, availability, yeah.
So we've got, there's some people on the team who have built optimizations for what they should do with batteries bidding into those things. We've done a bunch looking at big power loss events from the data's perspective. And I'd say the only other thing is it's on my to-do list. I have been asked to incorporate some of the FCAS price prediction stuff, augment that along with some of the energy market price prediction machine learning stuff I've been doing as well. So I haven't done anything in ML with that at the moment, but yeah, but a lot of the times we'll just dig into that to understand events that have happened.
Just a quick question. What what Python package were you using?
So yeah, that's a good question. So in this case, I used a package called GrobyPy. So Groby is it's a commercial solver that we use because we solve some really huge optimization problems, and the difference can be quite big. I think this is part of the reason as well why a lot of the cutting edge stuff is commercial as well, which is part of the reason I think people haven't played with it. That said, if you're interested in linear programming, I'd recommend there's a Python package called Pyomo for formulating these things, and there is the best open source solver is a program called HISE that's being developed by researchers at the University of Edinburgh. And so you can hook those together. I've built a lot of stuff with Pyomo and HISE combined together, and in fact, that would probably be my recommendation if you're interested in linear and mixed integer programming. Start with that, show that, see that it works for the problems. Then if you're like, wow, I really like solving, it's really good at solving this problem, I want to scale it up to now be a month or a year, then you may go, there may be enough value there in the better answer to then go to a commercial. Everyone. We do a lot of work for state and federal government departments, but we also do work for power stations and operators and things like that around. Cool.
Please bear with us. Hopefully you can still hear the speaker over the noise. Please help yourself to pizzas. John, pizzas for me. See you in 5 minutes.